In 1928, Paul Dirac discovered an equation that predicted antimatter before anyone had observed it. But hidden in that same equation was something even more profound that physicists ignored for 70 years. Dirac's equation implies that reality has one less dimension than we perceive. The three-dimensional world you experience might be a holographic projection from a two-dimensional surface. Dirac saw this in 1928, and nobody listened. Let me tell you the story of the most underappreciated insight in 20th century physics, and why it means reality is stranger than you can imagine. Dirac was trying to solve a problem that had plagued quantum mechanics since its inception. The Schrödinger equation, which describes how quantum states evolve, was not compatible with special relativity. It worked beautifully for non-relativistic particles moving slowly compared to light. But for particles moving at relativistic speeds, the equation gave nonsensical results. Physicists knew they needed a quantum equation that respected relativity. Several attempts had been made, but they all had problems. They predicted negative probabilities or negative energies, mathematical absurdities that couldn't represent physical reality. Dirac approached the problem differently. He insisted that the equation must be first order in time, meaning the time derivative appears only once. This was aesthetically motivated, but it led to something remarkable. To make the equation work, Dirac had to introduce four-component wave functions instead of single-component ones. These four components described something unexpected. Two components corresponded to a particle with spin up or spin down, but the other two components seemed to describe a particle with negative energy. This made no sense. Energy can't be negative. A particle with negative energy would be able to give away infinite energy and still have energy left over. The universe would be unstable. Dirac puzzled over this for months. Then he had a brilliant insight. What if the negative energy solutions weren't nonsense? What if they represented a new kind of particle, identical to the electron but with opposite charge, a positively charged electron? At the time, no such particle had ever been observed. Dirac was predicting the existence of something completely unknown, based purely on the mathematics of his equation. Most physicists thought he was indulging in speculation. The negative energy solutions were a mathematical artifact, not a physical prediction. But in 1932, just 4 years after Dirac published his equation, Carl Anderson discovered positrons in cosmic rays. They were exactly what Dirac had predicted. Particles identical to electrons, but with positive charge. Antimatter was real. Dirac's equation had predicted it. This made Dirac famous. He won the Nobel Prize in 1933 at age 31. The Dirac equation became a cornerstone of quantum field theory. Every student of physics learns it. It's one of the most successful equations in the history of science. But there was something else hidden in the Dirac equation that almost nobody noticed. Something about the structure of information and the nature of space itself. The Dirac equation describes a particle moving through three-dimensional space. But the way it encodes information about the particle is strange. The four-component wave function contains more information than you'd expect for a particle in 3 dimensions. In fact, if you analyze the information content carefully, you find that the Dirac equation behaves as if the fundamental information is encoded on a 2-dimensional surface, not in 3-dimensional volume. The 3-dimensional behavior emerges from this 2-dimensional encoding. Dirac himself didn't emphasize this. He mentioned it briefly in some technical papers, but he was focused on antimatter and the success of his equation for predicting particle physics. The dimensional reduction implicit in the structure of his equation went largely unnoticed. For decades, the Dirac equation was used as a tool for calculating particle properties. Nobody thought deeply about what its mathematical structure implied about the nature of space and information. It was just an equation that worked. Then in the 1970s and 1980s, physicists studying black holes stumbled onto something extraordinary. Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional to the area of their event horizon, not the volume enclosed. This was shocking. Entropy measures information. For ordinary objects, entropy scales with volume. A box twice as large can contain twice as much stuff and has roughly twice as much entropy. But black holes were different. Their entropy scaled with surface area. This suggested something profound. The maximum information that can be stored in a region of space is proportional to the area of its boundary, not its volume. This seemed to contradict everything we thought we knew about how information works in 3-dimensional space. Gerard Hooft and Leonard Susskind developed this insight into what they called the Holographic Principle. They proposed that the universe itself might work like a hologram. All the information in a 3-dimensional region is encoded on its 2-dimensional boundary. The three-dimensional physics we observe is a projection from this lower dimensional encoding. This was a revolutionary idea that seemed to come out of nowhere in the 1990s. But it wasn't out of nowhere. The mathematical structure was already present in the Dirac equation in 1928. Dirac had discovered holography 70 years before anyone recognized what it meant. Let me explain how this works. In a hologram, you store three-dimensional information on a two-dimensional surface using interference patterns. When you illuminate the hologram correctly, the three-dimensional image appears, but fundamentally, the information is two-dimensional. The holographic principle says reality works the same way. The three dimensions of space you perceive are projections from information encoded on a two-dimensional boundary, and this is not speculation. String theory, our best candidate for quantum gravity, explicitly realizes the holographic principle. The universe really is a hologram, and Dirac's equation told us this in 1928. The most concrete realization of holography is the ADS-CFT correspondence discovered by Juan Maldacena in 1997. This is a precise mathematical equivalence between a theory of gravity in a space with one shape and a theory without gravity in a space with one fewer dimension. A three-dimensional gravitational universe can be exactly described by a two-dimensional quantum theory on its boundary. Every event in the three-dimensional bulk has a corresponding description in the two-dimensional boundary theory. They're different perspectives on the same reality. This was shocking when Maldacena discovered it. But the structure was already there in Dirac's equation. The way the Dirac equation encodes information about particles in three dimensions corresponds to information on a two-dimensional surface. The holographic encoding was built into the mathematics from the beginning. Why didn't anyone notice this for 70 years? Because we were using the Dirac equation as a practical tool, not studying its deep structure. We calculated scattering amplitudes and particle properties. We didn't ask what the mathematical form implied about the nature of space. This is a common pattern in physics. We discover equations that work, that make accurate predictions. We use them successfully for decades. Then someone looks more carefully at the mathematical structure and realizes the equations were telling us something profound all along that we missed. Maxwell's equations unified electricity and magnetism and predicted electromagnetic waves. But Einstein realized they also implied the constancy of the speed of light, and thus special relativity. The deeper truth was hidden in equations people had been using for decades. The Dirac equation predicted antimatter, and everyone noticed, but it also predicted holography, and almost nobody noticed. We were too focused on the obvious implication to see the subtle one. Now let me tell you what holography actually means for reality. If the holographic principle is correct, if the universe is fundamentally two-dimensional with three-dimensional physics emerging as a projection, then space as we experience it is not fundamental. The three dimensions you perceive, the volume of space around you, the depth and distance, all of this is emergent. The fundamental reality is a two-dimensional surface encoding information. What you experience as moving through three-dimensional space is actually patterns of information evolving on this two-dimensional substrate. This sounds like science fiction, but it's serious physics backed by rigorous mathematics. String theory, loop quantum gravity, and other approaches to quantum gravity all suggest that space is emergent rather than fundamental, and the holographic principle is the clearest expression of this emergence. If space emerges from information on a lower dimensional surface, then asking what space is made of is like asking what a computer game landscape is made of. It's made of pixels and code. The three-dimensional world you see on the screen is a projection. The fundamental reality is the two-dimensional array of pixels. The universe might work the same way. The fundamental reality is information encoded on a cosmic boundary. The three-dimensional space you inhabit is how that information appears from the inside. You are a pattern in the hologram, experiencing the projection as if it were fundamental reality. This resolves several paradoxes in physics. One is the black hole information paradox I discussed earlier. If information is fundamentally encoded on surfaces not in volumes, then black holes don't destroy information. The information is preserved on the event horizon even as matter falls in. The holographic encoding makes information conservation natural. Another is the problem of quantum gravity. General relativity describes gravity as curvature of spacetime. Quantum mechanics describes particles and fields. Combining them seems impossible because they operate on different foundations. But if space itself is emergent from quantum information, then there's no fundamental conflict. Gravity is not a force in space. It's a property of how information on the boundary projects into the emergent dimensions. The holographic principle also has implications for consciousness. If you are a pattern of information in the hologram, then your subjective experience is this pattern knowing itself from within. Consciousness is not separate from the physical universe. It's how the information structure experiences its own coherence. This connects to my own work on quantum consciousness. If consciousness involves quantum processes, if it emerges from quantum information in brain structures, then it's participating directly in the holographic encoding. Your thoughts are not merely represented in the hologram, they are patterns in the fundamental information layer that projects as three-dimensional reality. Now let me address why Dirac didn't pursue this himself. He was aware that his equation had unusual dimensional properties. He wrote about it in technical papers, but he was focused on particle physics, on using the equation to understand electrons and positrons and their interactions. The technology of his time, the experimental capabilities, were not sophisticated enough to probe questions about the fundamental nature of space. These were philosophical questions, interesting but not testable. Dirac was a pragmatist. He worked on problems where mathematics could connect to experiments. He couldn't have known that 70 years later physicists would discover that black holes have holographic entropy, that string theory would realize holography explicitly, that the dimensional structure of his equation pointed toward the deepest truth about space and information. This is both frustrating and beautiful. Frustrating because we could have been thinking about holography decades earlier if someone had looked more carefully at what Dirac discovered. Beautiful because it shows that mathematical truth has its own logic independent of our recognition. The structure was there all along, waiting to be seen. Dirac died in 1984, just before the holographic principle was formulated. He never knew that his equation contained this deeper insight. But the mathematics survived him and eventually revealed its secrets. This raises a profound question. What else is hidden in the equations we use every day? What other deep truths are encoded in mathematical structures we haven't fully understood? The equations know more than we do. They describe reality more completely than our current interpretations grasp. The Dirac equation is still teaching us things 96 years after it was discovered. First it taught us about antimatter, then it taught us about quantum field theory and the standard model of particle physics. Now it's teaching us about holography and the emergent nature of space. How many other equations contain insights we haven't yet recognized? How much do our mathematical tools know that we don't? This is one of the deep mysteries of physics. The equations seem to be smarter than the physicists who derive them. Let me bring this back to what it means for you. If the universe is a hologram, if the three-dimensional world you perceive emerges from two-dimensional information, then you are not what you appear to be. You are not a three-dimensional object moving through space. You are a pattern of information on a cosmic surface, experiencing itself as if it existed in three dimensions. Your depth perception, your sense of moving through space, your experience of distance and volume, all of this is the holographic projection interpreting itself. The fundamental you is encoded on a boundary. The three-dimensional you is how that encoding manifests. This doesn't make your experience less real. The hologram is real. The projection is real. You really are experiencing three-dimensional space. But fundamentally, beneath the appearance, the information is two-dimensional, and the third dimension emerges from how that information is structured. This is similar to how a movie is fundamentally two-dimensional images projected at 24 frames per second, but you experience it as motion and depth and continuity. The experience is real even though the substrate is different from what it appears to be. You are a movie playing on a cosmic screen, but you're watching from inside the movie, experiencing the projection as fundamental reality. This is what Dirac's equation implies, and what the holographic principle makes explicit. And here's the most remarkable thing. This is testable. The holographic principle makes specific predictions about correlations at different scales, about the maximum information density in regions of space, about subtle effects in the cosmic microwave background. We're beginning to design experiments that could detect holographic signatures in nature. We might be able to measure the graininess of space at the Planck scale and determine whether it has holographic properties. Within a few decades, we might have experimental evidence that the universe really is a hologram. If that happens, if experiments confirm holography, then we'll look back at Dirac's equation with even greater awe. He not only predicted antimatter, not only laid the foundation for quantum field theory, but also encoded the most profound truth about the nature of space itself, all in one equation, published in 1928, buried for 70 years, now recognized as perhaps the deepest insight into reality we have. Dirac was a quiet man who avoided publicity. He was known for speaking very little, for thinking deeply, and saying only what was necessary. He would have been amused, I think, to know that his equation was teaching us things he never explicitly recognized. The mathematics knew, the structure contained the truth. We just needed 70 years to understand what Dirac had actually discovered. This is the power and mystery of mathematical physics. The symbols on the page capture reality more completely than our words or concepts. The equations endure long after their creators are gone, revealing new layers of meaning as our understanding deepens. Dirac gave us a tool that predicted antimatter, described electrons and positrons, unified quantum mechanics and relativity, and hidden in that same tool was the blueprint for holography, the secret that reality has one fewer dimension than we perceive. He was a genius not just because he solved the problem he set out to solve. He was a genius because he discovered something so deep that it took the rest of physics 70 years to catch up. His equation knew more than he did, and it's still teaching us. The universe is a hologram. Dirac told us this in 1928. We just weren't listening carefully enough. But the mathematics waited patiently until we were ready to understand. And now, finally, we're beginning to see what Dirac saw without fully realizing it. Reality is not what it appears to be, and the proof was there all along.